Alright, so example problem 4. We have a pendulum like this, and it's swinging around, and the first question we ask ourselves is this a linear system? Well, it might be hard to see at first, so let's solve the equation of motion. We have mg and the components mg cosine theta and mg sine theta, and then here we have maybe an input torque, and so our sum of torques is going to be equal to J. So torques is equal to J theta double dot. J is going to be ml squared for a mass a certain distance away from its rotation point, and our sum of torques is going to be our input torque, T, and our force of gravity, minus mg sine theta, and then our lever arm, L. Right, this is a force, and then this makes it a torque with the L. That's equal to L squared theta double dot. Okay, so solving for theta double dot, we get negative G over L sine theta plus T over ML squared. So this is not linear because they have a sign here. And a sine is not linear, a sine is sinusoidal. So nonlinear, which means we cannot put the system into a state space form, or the matrix state space form. We can't do this, where I'm using T instead of U here because T is our input. You're more familiar with U, but our input is a torque, and then we call it T, so I'm going to do that. We can't do this because this is for linear systems. And we have a non-linear system. So you can just write out the state space form as a bunch of equations. So first we'll make our states. So our highest derivative is theta double dot. And all of our states are everything you integrate out of theta until you get to theta. Everything you integrate out of theta dot until you get to theta itself. So we have theta dot, and that can go into theta. So these are our states. Another way of thinking about states is when you make your MATLAB model, or your Simulink model, the states are what comes out. Sorry, I don't know why the video stopped there, but I think I'll pick up where it stopped. So another way of thinking about states is through a Simulink model. So your states are what's coming out of the integrator blocks. So we have like 1 over S here, 1 over S, and then you have stuff going back into summation, and what's coming out is your theta double dot. That's how MATLAB sees it. So it's looking at what's coming out of these integrator blocks. It's a state. So states are theta, dot, and theta. And so we will assign our state space variables to those. So our x1 is always our lowest order state, which is theta. x2 is always the derivative of the state, theta dot. That means that x2 is also equal to x1 dot. x2 dot is equal to, well, our equation of motion. Negative G over L sine theta plus T over ML squared. Okay, so what is our state space form? Our state space form is when we have the state derivative on one side of the equation and the rest on the other side. So our first state derivative is x1 dot. Our second state derivative is x2 dot. x1 dot is equal to x2, you always express your state derivatives in terms of your state variables. So these are your state variables, right? x2 dot is negative g over L sine x1, right? Because x1 is equal to theta, t over ml squared. Okay, this is your state space representation. So why do we do this? Well, we start off with the second order equation, theta double dot equals negative g over L sine theta minus t over ml squared. And we like first order equations, but we can't directly put this into first order equation. We need to make a system of equations if we want to do that. So what we do is we, instead of seeing theta double dot as a second derivative of theta, we see it instead as a first derivative of like a angular velocity, omega, right? And we know that x2 is equal to that, right? That's the same as theta dot. Sorry, omega is just by itself. Wait. Instead of seeing theta dot double dot as a second derivative theta, we see it as a first derivative of like an angular velocity. So our angular velocity is theta dot, otherwise known as omega, right? Otherwise known as x2, right? So we change these out. We change these out so that way we go from the second order of a displacement to first order of a velocity. And I know it seems kind of wonky to do this because it's still a second order system, but mathematically you can treat it as two first order systems. And so what you do in your state space is you assign these state variables to your equation. And so, like we said, we've reduced this order because now we are representing a second order displacement into a first order velocity. But now we have two different variables, right? Where we have a variable for displacement, right? And we have a variable for displacement, which is x1, and we have a variable for velocity, which is x2. So we need to relate the two, and that's what this guy does. It says, oh, the velocity is the derivative of displacement. So just to say that once more, instead of expressing our system as a second order system, we reduce the order of this guy, right? Instead of a second derivative of displacement, it's a first derivative of velocity. And then we say, oh, well then, now we have two variables. How do we relate them to each other? We say, oh, the velocity is the derivative of displacement. Okay, moving on to equilibrium. So this is state space, right? Moving on to equilibrium, we have I just saw your email. Moving on to equilibrium, we know that equilibrium occurs when our object of interest is not moving, right? So if we have our pendulum, where if we were to place the pendulum, would it just stay there? And conceptually, it makes sense that if we place the pendulum at theta equals 0, and we just let it sit there, like we don't have an initial velocity. So theta equals 0, theta dot equals 0, then it's at equilibrium. It's not going to go anywhere. Likewise, if we put it at theta equals pi, and theta dot equals 0, right, we're assuming this is stiff. It's kind of rod. If that is placed at pi with no initial velocity, then it's not going to go anywhere. It's at equilibrium. So this is conceptually what we expect to happen. Let's solve for it mathematically. So we know that equilibrium occurs when the derivatives are equal to 0. So that's theta dot equals 0, theta double dot equals 0. In our state variables, theta dot is equal to x2, and theta double dot is equal to x2 dot. It's also equal to x1. Right? So we can go and replace our state space derivatives with 0. So we have x2, here's the equations, right? And x2 dot equals negative g over L sine x1 plus t over ml squared. Right, these go to 0. We're going to guess that our torque is going to be 0 at equilibrium, which makes sense, right? If we place it here and t is some value, non-zero, it's not going to be at equilibrium, so we're going to guess that t equals 0 as well. So this goes to 0. So then we have 0 equals negative g over L sine x1. The g over L we can cancel out, and we get x1 equals 0 pi 2 pi. And that's exactly what we expect to have happened. So our equilibrium values are 0, 0, and pi 0. So this entry is theta. This is theta dot, theta, theta dot, otherwise known as x1, x2, x1, x2. Okay, let's talk about linearization. So we've found state space, we have found equilibrium points, and now let's talk about linearizing the equilibrium points. Oh, before I move on, I'll mention that to double check your equilibrium values in MATLAB, you use the trim function. Okay, and then I'll talk about how to double check the linearization in MATLAB later. So to linearize a system, we find the Jacobian of the system about the equilibrium point. The Jacobian is defined as df1, dx1, df1, dx2, df2, dx1, df2, dx2. So we know what x1 and x2 are, but what the heck are f1 and f2? So we'll look at our state space equations again. Right, f1 is the first derivative of the state, f2 is the second derivative of the state. If you had more equations, like you do in task 4, right, you have 2 more here. f3 would be that third derivative, f4 would be the fourth derivative. But here we just have a 1 degree of freedom second order system, so we have 2 equations. Right, and also on task 2, your Jacobian will be a 4x4 matrix. Right, whereas here we only have a 2x2 matrix. Okay, so to find the Jacobian about the equilibrium point, we just do the partial derivatives. So df1 dx1, right, df1 dx1 is 0 because there's no x1. df1 dx2 is 1, right, because it's just the derivative of this with respect to x2 is 1. df2 dx1, this is a little bit more involved, right? So we're looking here. The partial derivative f2 with respect to x1 is negative g over L cosine x1. We're evaluating at the equilibrium point 0, 0. You could also pick pi 0, but we're going to start with 0, 0. and that's equal to negative g over L, because cosine of 0 is 1. And then lastly, df2 dx2, we don't see a dx, or we don't see a x2 in here, so that's 0. And that, believe it or not, is your Jacobian, and it's also your A matrix in the state space form x dot equals ax. So remember how I said this is only for linear systems? Well, what you've done is you found a linear approximation about the equilibrium point. In other words, you have your pendulum, right, and it's at equilibrium down there, and if you just do small deviations, right, theta dot theta, they're about 0, then this linear model is pretty accurate. And we like linear models because they're easier to work with. But what about B, right? Don't we normally have BU here? Or I guess in this case it would be BT. Well, to do that, you just do df du. So partial derivative with respect to u. df1 du, df2 du. For the first one, we note that there's not an f here, right? So this is 0. The partial derivative here with respect to t, so I said there's no u here. There's no t here. The partial derivative for f2 with respect to t is 1 over ml squared. So what we've done, that should be t, is found the B matrix. So now we have x dot equals a x plus b t. This is our linearized model. Okay, so I'll leave you to do task 1 and 2. Please email me if you have any questions.